So in this video, I'm going to talk to you all about reaction rates. Now, the rate of reaction is just how quickly it happens, and lots of things can affect the rate of reaction to either make the reaction go faster or slower. The rate of reaction is defined as the change in concentration, which we can think of as the amount of something, of a reactant or product over time. So a simple way we can represent that is simply that the rate of a reaction is equal to the amount of the reactant or product either used up or formed over the time that it is used up or formed in. So in order for a reaction to occur, particles have to collide. They have to hit each other in order for a reaction to actually happen. Now, they have to collide with the right orientation and also with the right energy. So particles in a solution are always moving around and always bumping into each other. So if we've got a bimolecular reaction here, where we've got a molecule of AB and a molecule of CD coming towards each other and colliding, we have two options. Either they don't collide with the right orientation and don't have enough energy and simply bounce away again. Now, this is the likely scenario. They will bounce into each other and they will move away again without having reacted. So you'll get AB still on the left and CD still on the right. This is just to point out that they do not react every time they hit each other. They need the right conditions for a reaction to take place. So let's pretend they do collide with the right orientation, so facing the right way, the right direction, and they collide with a certain amount of energy needed, known as the activation energy. Then we can get a reaction occur. So here the particles collide and they bounce away again, and now we've had a reaction occur. So we've now got a molecule of AC and a molecule of BD. So by having enough energy for a reaction to happen, what we mean is that they need the minimum amount of kinetic energy required to start the reaction, which is called the activation energy. So if we have a look at an enthalpy profile diagram, where we have the enthalpy on our y-axis, and on our x-axis, we have the progress of the reaction. Now, our reactants start off with a set amount of energy, and then we need to provide energy in order to break the bonds of the reactants. And this starts the reaction by getting the reactants into an unstable intermediate state. In order to do that, we need to give them energy to break their bonds. And then once the bonds are broken and they are in this reactive state, then the reaction can actually occur and we can move to our products. Now, our products obviously could be lower in energy or higher in energy than our reactants based off whether it is an endothermic or exothermic reaction. And here we have an exothermic reaction. As you can see, the delta H is negative. Our products have a lower energy than our reactants. So we can just label this up. Products. Here we have our activation energy. So we can label this as EA. And unless we have this activation energy, unless we have this required energy, the reaction simply won't happen. If you think about pushing a car up this hill, you need to get it all the way to the top to get it to go down the other side. If you only get it up halfway, then it will fall back down the hill. AKA, we will move back to our reactants unless we have the required energy to go all the way up to break our reactant bonds and move all the way down to our products. So reactions with low activation energies often happen relatively easily, but reactions obviously with high activation energies, you can imagine don't, as there will be less particles with the required amount of energy in order to react. Now, if you want a reaction to occur that isn't occurring at, say, room temperature, you can make it more likely to occur by heating it. Now, next we're going to be talking through Maxwell Boltzmann distributions, and we can see how heating a mixture increases the likelihood that we will have the required activation energy, and so we are more likely to get a successful reaction. So this is a Maxwell Boltzmann distribution. In this Maxwell Boltzmann distribution, we are shown the likelihood that a molecule will have a certain amount of energy at a certain temperature. So imagine you are walking down a busy street. You'll see some people moving slowly. You'll see some people running very quickly, but most people will be walking along at a normal pace. And that's exactly what we see here. We see some particles having very low energy and moving very slowly. We see most particles are moving with a moderate amount of energy, and we see some are moving with a very fast amount of energy and whizzing around. Now, the graph here starts at 0, 0. This is because if we have zero energy, if we have zero kinetic energy, we are not moving at all. And unless we are at 0 Kelvin, then all molecules will have at least some kinetic energy. We will be moving with some speed. So the area underneath this curve is equal to the total number of molecules in our system. So you can see here we have the most likely energy being somewhere in between the two extremes. If we are to increase the temperature, then we shift the curve to the right, meaning that more molecules have a higher energy. Now, before we do that, we can see here in the blue that we've got our activation energy barrier drawn into this graph. Now, that means anything to the right of our activation energy will have enough energy to react if a collision occurs with the right orientation. So let's watch what happens if we increase our temperature. So let's say that this one was, say, 298 Kelvin. And let's say that the one that we're going to draw in the green is equal to 330 Kelvin. The temperatures don't matter so much. We're just showing what happens when we increase the temperature. Our activation energy barrier hasn't changed. We haven't lowered that. All we've done is increase the number of molecules with a set amount of energy. Now you can see by increasing the temperature, we've increased not only the most likely energy of our molecules, which is now higher, but we've also increased the area underneath the curve past the activation energy barrier, which means that more molecules now have the required energy to react if a collision occurs. This makes it more likely that a successful reaction will occur. Thinking back to collision theory, you can think of it as a statistics game. So if you have so many collisions per second, If you increase the number of molecules with the required amount of energy, then a higher proportion of those collisions per second will be successful, as a higher proportion of the molecules will have the required amount of energy. So when you do get a collision with the right orientation, it will be more likely to be successful. Now, on this same diagram, we're just going to draw on what happens if we have a catalyst present. So when we have a catalyst present, we know that we lower the activation energy barrier by providing an alternative pathway for the reaction with a lower activation energy. And so that means that if we draw on a new activation energy here, so this is our EA with a catalyst, you can see now that even more molecules have the required amount of energy in order to have a successful collision, no matter what temperature we're at. So the catalyst speeds up the rate of reaction because it means it provides an alternative pathway with a lower activation energy, meaning more molecules have the required amount of energy for a successful collision, making it statistically more likely that two molecules with the correct activation energy will collide with the right orientation. Now, when you're asked to draw out these Maxwell Boltzmann distributions, and you're asked to draw one for a certain temperature and then one for a higher temperature, say, just make sure that you draw the higher temperature with a lower height than the first temperature. This is because you're shifting, the number of molecules in the system doesn't change, so the area under the curve should still be the same. So if you're increasing the area towards the right-hand side, you're increasing the number of molecules with higher energy. That means there will be less molecules with a lower energy, so you need to balance out that area under the curve by lowering the height of the curve. Now, if you are wanting to go to a colder temperature, if the question asks you that, you need to draw a higher curve at a lower temperature, and then a lower height at higher kinetic energies. So we've got a higher height with lower kinetic energy and a lower height with higher kinetic energy. You can see from what we said previously now that actually less molecules have the required amount of activation energy, and so this makes it less likely for a successful reaction to occur, because it's less likely you're going to get two molecules collide with the right activation energy. So when we've got our factors that affect the rate of reaction, some of which we've already been through using the Maxwell Boltzmann distribution, we need to know how they affect the rate of reaction, going back to collision theory. So for temperature, we said increasing the temperature will give molecules more energy, more kinetic energy, and so they'll be moving faster. If they're moving faster, this means they're more likely to collide into each other. You'll get more collisions per second. Having more collisions per second means statistically you're more likely to get a successful collision each second. Also, increasing the temperature, we said, increases the number of molecules with the required activation energy, which means out of these increased collisions, you're more likely to get a successful one because now also more molecules have the required amount of energy needed to react. So increasing concentration or pressure, I've grouped together as the answer is pretty much the same. It just depends on whether you're talking about a solution for the concentration or a gas for the pressure. So increasing the concentration means that the particles on average will be closer together. If they are closer together, they'll collide more often. And if the collisions are more frequent, we've already said this means there's more chances to react, which means you're more likely to get a successful collision. The pressure is exactly the same. Increasing the pressure means that you lower the amount of space that the gas has effectively, and so you're pushing the gas more closely together. So this means they're more likely to collide. You're getting more collisions and therefore more successful collisions. So when you're answering a question on this, you're going to find yourself saying the same things over and over again. That's completely fine. These are all the same points because you're relating them all back to collision theory. More collisions means more chance for a successful collision. Higher energy collisions also means more chance for a successful collision. Now, a catalyst we also went through with the Maxwell Boltzmann distribution, but remember we define a catalyst as something that increases the rate of reaction by providing an alternative reaction pathway with a lower activation energy. So the catalyst is chemically unchanged at the end of the reaction also. Remember, it's not used up in the reaction. So they're great, a catalyst, because they don't get used up in a reaction. So you only need a tiny bit of a catalyst to actually, create a huge amount of difference. They do take part in the reaction, but because they're remade at the end, they're not in the overall reaction equation. But remember, catalysts are very, very fussy about what reactions they actually work with, and they often actually only work with a single type of reaction. Because the catalysts allow us to make the same amount of product faster, and often at a lower temperature, because they provide a lower activation energy barrier, meaning we don't have to increase the temperature so much to increase the amount of molecules with the required amount of activation energy. Because of these reasons, catalysts often save industrial processes loads of money. So whenever you talk about catalysts in a question where you talk about industry, make sure you mention that they are not only saving time by making the reaction occur faster, but they're also saving money. And time is money, so it all works out anyway. So we've got 3 different ways that we need to use or be able to describe how to use to measure the rate of a reaction. So we can either use light to do this. So in a reaction that, say, forms a precipitate, we can see how much light passes through the solution at the start of the reaction when there's no precipitate. The light, 100% of the light should pass through the solution. As the precipitate forms and we get more of the blue, eventually the solution will be so cloudy that you won't be able to see the X underneath the solution. Now, when this happens, you stop the stopwatch, and that is the amount of time your reaction took to complete. Now, if we want to do this quantitatively, because doing it qualitatively, where we see the X disappear, we may end up bringing error into this based off who is doing the experiment. Some people may argue they can still see the X, whereas others are adamant that they can't see the X anymore. So if you're having that trouble, then you could suggest to use a colorimeter instead. So the colorimeter measures the wavelength of light that is passing through a solution. And as the precipitate forms, we will get less and less light passing through the solution, and we'll be able to plot a graph from this of the amount of light going through decreasing over time, giving us our rate of reaction. Now, in reactions where we produce a gas, we can either measure the mass decreasing, or we can measure the amount of gas produced over time. So in your mass decreasing, you would have, say, a metal reacting with an acid, giving off hydrogen gas. As the hydrogen is leaving the solution and bubbling away into the air, it will decrease from the mass of your overall solution. And so you'll see the mass decrease over time. You can plot this on a graph showing the mass versus the time. It will decrease, and you can get your rate of reaction from that. Or we can measure the amount of hydrogen being produced over time. By doing this, we attach a syringe to our flask, and we can see the syringe being pushed out over time as more and more gas is produced in the syringe, or more and more gas from the reaction that's being produced in the reaction goes into the syringe. So this gives us the amount of hydrogen produced over time, again, allowing us to plot a graph and get our rate of reaction from that.